Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Michael Francis from London, but from London, Ontario, not London, England. And he will tell us about some transverse orientation class of certain singular foliation. Michael, the floor is yours, the Zoom is yours, take it away.
Well, thank you very much, Piotr, for that introduction. And thanks for the clarifying remark about which London I'm from. That's always a useful thing to do. Yeah, it's been super nice staying here at I've never been before. And yeah, it's been terrific hospitality. So thanks very much. As you can see on the slide, I hope, title is the Transverse Orientation Class of Certain Singular Foliations. So I'm going to do something that maybe it's a little bit, I'm going to really travel back in time and talk about some things that I did during my PhD thesis and something I'm currently doing, which is kind of a continuation of that. So I've had to kind of remember some things. So let me start by showing some references that will hopefully kind of show how I arrived at these thoughts. So it all kind of begins, let me just practice. Okay, so with this construction due to Kahn of transverse fundamental class and orientation class as well for foliations. So this is something I had read a long time ago and had in the back of my mind. And when it came time to sort of choose a PhD project, I got kind of shunted towards this this nice work of Androlodacus scandalis on the holonomy groupoid of singular foliations. I got familiar with that work and eventually wrote this thesis, which is very sort of example driven. I isolated some specific family of singular foliations and tried to sort of understand the content of Androlodacus scandalis's work for this class of examples. And if you want references for that, it's sort of split up. Easiest thing for me to do is link archive IDs. So these are essentially the different pieces of my thesis. One of these, I think, is published. So I have to go back to here if okay.
Sorry, but I find many leaves.
Yes, that's a very strange thing. So good remark.
What?
Yeah, a strange thing indeed. But we'll see shortly. So some other relevant references is this work on sort of Thom isomorphism for cross products and counterpart in cyclic theory due to Kahn, Elliott, and Sumi Nast. So let's see. So the holonomy groupoid. This was introduced by Vinkeln Kemper. Given a regular foliation, you can kind of create this nice groupoid. And in basic cases where the quotient by the foliation makes sense and is a nice space, this groupoid, this holonomy groupoid is equivalent to the manifold of the foliation mod the foliation, so the space of leaves. And kind of typically that space of leaves is something very poor that you can't really study or do analysis on. And this holonomy groupoid is sort of the correct proxy object. So when you're working with the holonomy groupoid, morally what you're doing, or trying to do anyway, is work with this space of leaves, which may not be amenable to direct analysis.
I have a question.
Yeah, please.
Speaking about the leaf space, you mean only the condition of the leaf space, or that this foliation is by fibers of some submersion?
Yeah, so if there is some surjective submersion and the fibers, the leaves of the foliation are the fibers of that submersion, then you can form this quotient and it's the target of the submersion. And in that case, this groupoid is sort of no better an object than that quotient itself for sort of studying. But it's more robust. Even that leaf space is poor, you still have this groupoid. And many authors have worked on, so this is all in the regular setting, regular foliations. Many authors have worked on extending these constructions to work for singular foliations. And the construction I'll be concentrating on is that of Androdacus Scandalis.
Sorry, will you explain the difference between a foliation and a singular foliation?
Yes, we'll come to that a little bit later if that's okay.
Yeah, surely.
So, but roughly speaking, sorry, I'm not sure if you're seeing what I'm seeing.
Yeah, we are seeing that you minimized.
The plus on the right,
Maybe
bottom right corner, you
no
Bottom right corner.
have size control.
size.
Okay.
Yes.
Okay. Yeah, just to say something, you know, if you think of something like concentric spheres in R3, so the typical pieces of that partition are two-dimensional manifold spheres, but there's some exception at the origin where there's a piece of the partition that's zero-dimensional. And at least at a kind of intuitive level, a singular foliation is something like that, where you have dimension drop phenomenon occurring with the leaves. Okay, so what was in this article of Kahn that I mentioned? So if you have a regular foliation and you're looking at this polynomial groupoid, well, if you're in a special, I'll just look at this special case. So there's some sort of transverse orientation. You can try to think about what that probably means. You're not sure. And a codimension 1 foliation. So the leaves are hypersurfaces. And there's a transverse direction, which is sort of one-dimensional. Then this polynomial groupoid sort of wants to be an oriented one-dimensional manifold. That's what it would like to be if the quotient made sense. And you know, in keeping with the fact that it would like to be an oriented one-dimensional foliation, Kahn constructed these things which ought to exist if you're basically looking at an oriented real line. So he constructed this transverse orientation class, which lives in K1, and this transverse fundamental class, which is a cycle-cocycle, also of dimension 1. And in the case where the groupoid is sort of as good as the quotient, and you just have sort of the line, these are the kind of expected objects. Is that kind of okay? I don't have, this is sort of just background. So, is there more here? Yeah, and moreover, these classes, so there's a pairing between these groups, and the pairing of these elements is non-trivial, which gives you a theorem that this orientation class in K-theory is non-torsion, which is always exciting when you can prove that a K-theory class is non-zero. It's sort of like you've found a non-trivial vector bundle on your space, your kind of non-commutative space. Okay, and I guess I'm going to outline how Kahn did this. And if it's possible to sort of vaguely remember this in the back of your mind, that would be good, because later I'll be trying to do something sort of inspired by this. So what Kahn basically does is he takes a complete transversal, so some one-dimensional curve that meets all the leaves of the foliation. I don't know why that's blank. And then the first thing you can do is you can replace this holonomy groupoid by its restriction to this transversal. So that gives you a simpler groupoid, which is equivalent to the original one. So this is a common sort of game to play in groupoid context. This transversal is an oriented manifold of dimension 1, and it does have an orientation class, a fundamental class. And the orientation class, it's this K-theory class, can be mapped into the K-theory of the groupoid just because the unit space of this restricted groupoid is T, and you have this Starmer homomorphism, it's an inclusion, And at the level of K theory, you can induce a map. So whatever your orientation class is here can be mapped to some K theory class here. And that's how the orientation class can be constructed. The fundamental class is the more difficult thing to construct, but the idea is sort of the same. Here, you have a fundamental class, which is given by this sort of formula that sort of realizes integration along T. I mean, this is the thing that will, give you like the winding number invariant when you pair it with K1. And that thing lives only here, and you need to find a way to extend it. So this one trace makes sense on the. I've written two trace, but I guess this is a one trace. I guess there's a typo here. It should say one trace. But that one trace should be somehow extended from where it lives to the ambient algebra. And as long as you can do that, you're kind of home free. You have now something you can call fundamental class, something you can call orientation class, and sort of by naturality, they pair the same way that they pair here, which is to give one, as sort of winding number of a loop is one. Any questions? So just sort of a sketch a little bit if you.
I have a question about this GT. So this is this holonomy groupoid.
So this is the holonomy groupoid restricted to a transversal. So if you're thinking of something like, a cylinder that's been foliated into sort of spirals or something like that, then what we're doing is we're choosing T to be some, line that cuts transversely along all the spirals. And these spirals, they all meet that line that I'm calling T. So you can kind of look at a smaller groupoid instead of, using arrows that communicate between, points on the same leaf in the whole ambient manifold. You're just going to take the arrows that communicate between points on this line. So it sort of discretizes everything in sight. Now,
Yes.
you have a point on this transversal, and you have arrows to a discrete set of points that lie on the same spiral. So sort of the arrow direction of the groupoid gets discretized.
But this groupoid is non-abelian, right?
Non-amenable?
No, non-abelian. It's non-commutative.
Non-abelian. Yes, typically, yeah.
So you map this into the center of that convolution sister algebra.
So arrows in this groupoid are very well known in the theory of differential equations. It's called the Poincaré Camberg.
Yeah, it's like a sort of first return map, and you could be thought of that way in this. Poincaré map. Okay, so let's see. So let's go to the singular case. That was just throwing some of the ideas around from the classical setting that are going to be relevant. But now let's come to the singular setting. So here's this definition that I'll work with. So Stefan's Sussman foliation of M is defined to be a collection of vector fields on N. So these vector fields essentially should play the role of the vector fields that are tangent to the leaves. So if you're thinking of foliation as space partitioned into nice sort of submanifolds in some way, when you have that picture in mind, you have vector fields that are respecting these submanifolds. And that's what this F is sort of trying to capture. So we'll define foliation to actually be a family of vector fields. And the axioms are that it should be closed under the bracket, which it ought to be because of the Frobenius theorem. And locally finitely generated, which means sort of you can write down a finite collection of vector fields, essentially, which give you all the tangent directions. You just need to take multiples of these, smooth function multiples of these to generate all the leafwise vector fields. Once you have the vector fields, you can talk about leaves. So when are 2 points in the same leaf? Well, if you can get between them using these vector fields. So you start composing the flows of these vector fields and you generate equivalence classes in that way. And the basic theory, so classically in this sort of regular foliation case, this family of vector fields, when you do this process defining leaves in this way, you'll break up M into leaves all of the same dimension. But I haven't really done anything that will guarantee that in this definition. And Stefan Sussman proved that these conditions at least suffice to guarantee that the pieces you're going to get are submanifolds. I guess that's a little buried in this statement, but I say possibly varying dimensions. Well, I guess I mean the dimensions at least make sense. So the leaves that you will get from the Stefan Sussman foliation will be immersed submanifolds, maybe not all of the same dimension, but they will be immersed submanifolds. There's sort of a picture here of something you might see. Some cylinders collapsing to a line.
So from this picture, one could expect that you obtain some stratification.
Yeah, this is sort of a...
And when people are speaking about stratification, then they study some properties of the stratification, like.
Yeah, I believe this sort of stratified space kind of fits into the well, sort of smooth stratified space usually fits into the.
So the result is that you obtain some kind of stratified manifold with
if you like
regular strata.
There are certainly connections, but as you'll see, the partitions I'm going to look at are going to be very boring. So what's actually going to matter is the sort of dynamical information. So something that's buried in this definition, and then maybe I'll just say it now, is that so there's basically a map now, like given an F, I get a partition. But who's to say that two different curly Fs can't yield the same partition? So this definition sort of departs from the classical idea of a foliation, which you sort of think of foliation as a partition. But here we're also sprinkling some kind of dynamical data onto the partition. So we're going to remember which vector fields induced it. And there can be different collections of vector fields inducing the same partition. And the partitions I'll consider will be, as you'll see.
So excuse me, just to be sure, yeah. So this is the theory of distribution. You are selecting distribution of your tangent space to build up for this.
So there is also a distribution here, but the distribution also doesn't capture everything. The vector fields. So there are, I guess, three ways to think of foliation. You can look at the collection of leafwise vector fields, or the collection of sort of tangent planes, or the leaves themselves, so the pieces of the partition. And classically, there's no difference. You don't care. They're all kind of equivalent data. But in this context, I think, I guess, the distribution or the partition would be the same data. But this is additional data. This collection of vector fields is something that you can't get back from the partition. You maybe given the partition, you can try to find like a largest family that induces it. Just take all the vector fields that are sort of tangent to the partition, sort of try to enlarge it into a maximal thing. But you could do that, but I do want to allow for a variety of families of vector fields to induce the same partition. Okay, so this definition is the one that Androladakis Skandalis used when they gave their construction, not the only construction, but their of singular foliation. It's a very general definition, and in general, their groupoid is quite pathological potentially. It might not be a Lie groupoid, which is what you're sort of hoping for. And the conditions for it to be a Lie groupoid are well understood. So it's a Lie groupoid if and only F is sort of a so-called almost regular foliation, which by definition means that all of these sort of fibers in the sort of I don't know, algebraic geometry sense are all of the same dimension. So here this IP stands for the ideal of functions vanishing at P. So if they're all of the same dimension, then F is kind of like projective basically, and it's dual to a vector bundle, which can be given a Lie bracket. And so basically it's another way to think of this, if you like, is that F is a Lie algebra. It's the sections of a Lie algebroid, so there's some correspondence. Those are the conditions for the groupoid to be a Lie groupoid.
So sorry, so to understand this condition better, if this module was locally free,
Yes, it's
then
actually,
it would imply regularity. So the
in fact, no.
because then it would be the vector bundle, which is a sub.
Yeah,
But it's a distribution which is a vector sub bundle, the tangent bundle. So that by the Frobenius theorem, it would imply regularity.
yeah, but it doesn't, it's not, so because when you say locally free, it just means sort of as an abstract C infinity M module. So yes, there will be a bundle, but there's nothing to say that that bundle will be a sub bundle of the tangent bundle. In fact, what you'll have is a map from the bundle that you get from biduality to the
non-injective.
to the tangent bundle, probably non-injective. And that's basically the reason why this is something bigger. We're not just talking about regular foliations when we say this. There's some sort of distribution that's smooth that covers it, but I shouldn't really say distribution because it's not really living on the manifold, but we can cover it with a smooth Lie algebroid that will then map down to a still singular distribution. I don't know if that made sense, but I think that maybe if I switch slides, there's some example here, just to give you an idea of how big this basket is. Stefan Sussman foliations. Any action whatsoever of a connected Lie group would give a Stefan Sussman foliation, whose leaves are the orbits of the action. So you just take the sort of vector fields that drive this group action, and those generate your family F. And okay, so what do the leaves look like? Well, they're the orbits, and the orbits of a general Lie group action can be pretty nasty, pretty far from what you think of when you think of a foliation, is what I mean by nasty. And the almost regularity, well, a sufficient condition is that the isotropy is very rare. So if the set of points with trivial isotropy are dense, then you're going to have an almost regular foliation induced. And actually, you can say exactly what the Androlodocus scandalis groupoid would be in this case. It's just going to be this action groupoid. I don't know why it was H to begin with, and it became G later. So there's a typo there. The Lie group is H, so it should be H transformation groupoid M.
So this is isomorphism, it's not equivalence. What is equivalence?
It's isomorphism of Lie groupoids.
And what happens when your Lie group is disconnected?
Well, then you would sort of still have them. Well, then the thing is that the orbits don't need to be connected, for example. So you start here, you've added in arrows that communicate between like leaves that aren't path connected to each other, potentially. But yeah, basically within any disconnected Lie group, there's a connected one that's the component of the identity. And both of them will give the same foliation, because when you start talking about the vector fields, the fundamental vector fields for the action, they only care about the component of the identity anyway.
Okay, I've got you. Yes, yeah, thanks.
So you may as well
Clear.
By definition, leaves are always connected.
Leaves are connected. I mean, Androlodocus scandalis do all kinds of crazy things, so they allow, not necessarily source connected groupoids, but yeah, leaves should be connected. I think for most of us, that's a requirement. But then again, I'm throwing a lot of requirements out in this context. So leads will be connected for us. Oh no, I've done bad things again. Try to fix it. And I think, yeah, so every foliation in this talk is almost regular. So you don't have to worry about the pathology of, you know, like a diffeological groupoid. That's not happening. Everything is smooth. Everything is a Lie groupoid. So I read that paper of Androdacus scandalis, and I wanted to understand their definition. So I looked at the very easiest examples you could possibly imagine, where you take a vector field with one critical point on the line, and you generate a family, call it FK. So there are sort of two sort of possible dynamics, at least at the topological level, something like an Euler vector field or something drawn below that. And no matter which K you take, maybe I should say out loud. So another way to define this family FK is all vector fields vanishing to kth order at the origin. So there are different families of vector fields, but no matter which K you take, the leaves are not different. You have the half lines and you have the origin between them. And even though all those partitions are the same, in this formalism, F1, F2, F3, they're all different Stefan-Sussman foliations.
Do you have some invariants recognizing this?
Yeah, so we'll see how it
distinguishing
reflects.
like some multiplicity at the stratum.
Yeah, we'll see how it shows up in the groupoids and stuff. So I don't know what order this is going in, but I didn't really say too much about the C-star algebras, but you can take C-star algebras of the groupoids. So there's a baked into this construction of a holonomic groupoid is a construction of a C-star algebra. There are only two types, and they only remember the parity of K. They're basically all cross products for this sum. These are all transformation groupoids, where the action just differs in sort of the order to which it fixes the origin. And there are two cases, topologically speaking, for the dynamics, you get two C-star algebras. And a little
multiplicity is not topological. You are forgetting about multiplicity.
Yeah, the dynamics topologically, there are only two types of dynamics here, and the C-star algebra only cares about the sort of dynamics up to topological conjugacy. So only two answers are possible, and two answers do in fact occur. So these C-star algebras are not the same if you look at C0R crossed by these two actions. We could talk more about that, but I'll continue. And a little bit more interestingly, so I looked at the smooth algebras, and they are all different. But that's not really the story I want to tell today, but you can tell them apart by some sort of, I'm sure you can tell them apart by cyclic cohomological invariance, but the way that I sort of approached it was to analyze the sort of ideal lattice inside these algebras. But I think that could be formulated better.
Excuse me. By the sister algebra, you mean the reduced sister algebra or the universal one, which is?
Yeah, I mean, here there's no difference, I think, but generally there are choices to make. So I said the C-star algebra, but you're right. I mean, there are different completions of the, yeah. But here it won't matter. We'll all agree. Okay, so that was fine. I felt at this point like I basically understood these very simple examples. And I wanted to see what more I could do. So I did the next dumbest thing I could think of, which was to just add another dimension. So I did what I think of as a codimension 1 generalization. I took that family of foliations Fk and I crossed it with a trivial foliation with one leaf. So I introduced another direction. So before I had the origin was sort of a codimension 1 submanifold, you know, but now I'm taking a general codimension 1 submanifold. So let's read this definition. So I'm going to call transverse order K foliation a manifold that's partitioned into 3 pieces, positive half, negative half, and some hypersurface between them. Fine. But then there's also going to be a family of vector fields that induces this partition, curly F, the Stefan-Sussman foliation. And the condition is just sort of locally up to a coordinate change, you can make that family of vector fields sort of rectilinear, axis aligned. So up to a coordinate change locally, you're just looking at kind of the vector field we had before, getting away from the leaf and sort of parallel directions to the leaf. Does this definition make sense? Should I say more things? Okay. There are other ways of defining this class that are more minimal than this, but this is kind of what eventually fall out.
So this local structure suggests that there should be some resolution of this singularity. If you raise y to some power, this would give you a map which locally makes this singular foliation regular. So there's an image of some regular foliation under this map, which could be called a resolution of the singularity.
Yeah, there. I don't. That resonates with me a bit. I don't really have a comment. Yeah. Should I go on? Sorry, I don't have a response to your. Thank you for your report. So okay, so what the title is obviously not correlated to what's on the slide, but okay, so if you're looking at k equals 1, so things that locally look like vector fields sort of vanishing at the origin in the transverse direction, there's only one choice. You have to just work with all the vector fields that are tangent to your leaf L. But as soon as you go to K2 equal 2, there are infinitely many potential families that you can take that will satisfy this local triviality condition. This is probably showing a little more what's going on. So if you take the plane to be your manifold and L to be the x-axis, well, you could get that partition from these are basically the defining vector fields, like of the local trivializations. So this is sort of the flat example, if you like, I've called F1. Oh, by the way, this notation is bad. I guess Fk already meant something earlier, but now I'm just numbering these examples. So F1 is the sort of basic example. And then I have this other one where, I've changed the parallel vector field so that it sort of escapes the leaf at some linear rate. And even though they look different, and they are different, they're different families of vector fields, they're conjugate by some diffeomorphism theta that fixes the x-axis. So really F2 is just F1 written in another coordinate system. So the sort of takeaway is that talking about vector fields second order tangent to a hypersurface is not actually a sensible, you can't say that in a coordinate invariant way. I should actually keep like a watch on the time. What's the ending time for the
55. You have 55 minutes.
So we end at 6:55. How we use
45.
45. Okay, thank you. Okay, great. So let me just scroll forward. So then to do something a little more significant, I guess. So if we take the same example above, all these vector fields I wrote down are translation invariant in the x direction. So you could, instead of looking at them on the plane, you could look at them on a cylinder. So just make x a periodic coordinate. You can still talk about the same F1 and F2. Now, locally, this F1 and F2 are still the same because locally this map theta makes sense. So F1 and F2 are locally the same, which is basically the definition of F2 being a transverse order 2 foliation as I defined it. But that, it turns out, could not be done globally. They're different. They're sort of not even isomorphic for the natural notion of isomorphism of foliations, which, by the way, here is a diffeomorphism, which carries under push forward one family of vector fields to another family of vector fields. That's the natural notion of isomorphism of two-step-on Sussman foliations. So these are not isomorphic in that sense. So the first sort of so I wanted to see, I could see that there were multiple foliations, and I wanted to understand what's going on a bit better. And I was pleased to find this sort of holonomy thing. There's some sort of nascent holonomy, like it looks like the classical holonomy, but it's a little different. So if we are in one of these examples, transverse order K foliation, L is this hypersurface, and we have a curve. And you have little transverse slices. I don't know if I should be drawing a picture. Well, in the regular setting, we kind of know what happens. You have your leaf, and then you have transversals T0 and T1. And the fact that you have this curve C going between points on those transversals induces a germ of a diffeomorphism. A little piece of T0 will get mapped to a little piece of T1 by kind of doing parallel transport, sort of. You drag points along their leaves, and you get a germ of a map from T0 to T1. And this is basically hinting at the construction of the holonomy groupoid. Classically. Now, that doesn't happen here because, as you know, the leaves are just an upper half space and in a lower half space. So there's no sort of notion of dragging nearby points along the same leaf. They can move up and down sort of as much as they like and stay in the same leaf. You know, if I take a point here, you would think maybe move it around as much as you want. But in spite of that, if you kind of think this through, you eventually discover that there is some sort of leftover holonomy. You get a well-defined transformation here of these transversals at the level of Taylor series to order K-1. So even though you don't get a germ of a diffeomorphism from T0 to T1, you get up to K-1 Taylor series of such a diffeomorphism. So let me formalize this. So I'll write JK for the group of kth order Taylor expansions, orientation, preserving diffeomorphisms of R. So basically, Taylor expansions of maps to kth order. And I'm going to make them orientation preserving, so the derivative is positive. Operation on these polynomials is you compose them with each other and then chop off the extra terms. That's a Lie group. It's not a super complicated Lie group. It's certainly solvable. It's very close to being nilpotent. J2 is the same as the AX plus B group. And something that'll matter for us is that they have these extensions. So if you have a K-jet, kth order Taylor polynomial, you can take the K-1 jet, which means throw away the last term. And the kernel of that is a copy of the group R. So the K-jets that have a trivial K-1 jet are the ones which only have a coefficient in front of y to the K. And if you start composing these with each other, you'll see that it's the regular additive structure R. So you have these extensions, group extensions.
Y goes.
Is there a question?
No, it's y goes to, not t.
Oh,
Is the parameter, right?
yeah, that's
Y is the variable.
it's the map from the group R here. So I think it's correct.
Oh, yeah, from the group R, sorry, thank you.
Yeah, you're right. Y is like,
Yeah, okay, into the map y goes to, yeah.
so I have like a formal variation.
Sure.
So what does that do for you? So we have so the point one here is fairly easy to explain. So because of what I said on the last slide, you get some kind of holonomy map like this. So if you have a loop, so pi1 of L, you have a loop in L, then it will induce a jet transformation on the same transversal, which if you identify it with the real line, you can kind of identify that jet with an element of this group JK minus 1. And there are some choices there. You choose the transversal and so on. But anyway, so you get something like this. So what happens is that all of these invariants can occur. So what do I mean? Like if you have a fixed leaf L, well, like you fix the topology of L, and you've fixed a homomorphism to this jet group, you can devise a family F of vector fields that will cause this kind of holonomy map to be the target homomorphism of choice. So that's supposed to say, number 2 is supposed to say there are lots of these Fs, because you can sort of realize any holonomy transformation you want. And the third point is that it's a complete invariant. So basically, if you have 2 families, curly F, F and F prime, and their holonomy transformations are the same, then there's actually going to be an isomorphism between them. You'll be able to change coordinates so that one family is pushed forward onto the other.
You mean diffeomorphism?
Diffeomorphism, yeah. There's a little bit of fine print. So this HF is really only well defined up to sort of inner automorphisms of the target group, having to do with the fact that I didn't tell you what the base point on L is, and I didn't tell you, how to pick the coordinates of the transversal and stuff. And also, it's not an invariant of the global structure of the foliation because, M, the ambient manifold, could, I suppose, have topology, which isn't captured at all by this invariant, which only lives near the leaf. So the global topology of M certainly can't be recovered. This is really just talking about the structure of this family F when we look at a little tubular neighborhood near the leaf. So in fact, you could make the ambient manifold L cross R, and you would that would be a perfectly good kind of model. So that's kind of okay. So we understand what these foliations are, what's out there in this class, and now let's talk about what happens with the work of Ambulodatus scandalis. So what does the holonomy groupoid look like? Well, the only thing it turns out to depend on is in this third bullet point. So you have your holonomy invariant, pi1L goes into this group of jets, and there's the image, which I'll call gamma. So gamma is some countable subgroup of jets, k-1 jets, and we think of it as discrete. So we don't care about the topology of jk-1. There's just the image of this homomorphism considered as a discrete group. Gamma basically determines everything, this group. So I won't try to describe the full holonomy group because that would be needlessly technical looking, but not really any more interesting. But it's a Hausdorff-Lie group, that's true. Hausdorff is actually more interesting than you might suspect. Sorry, Lie groupoid, yeah. And if you restrict it to a transversal, okay, the restriction only depends on this group gamma. And what it is going to be is a certain smooth blow up sort of groupoid that I'm calling G gamma. And it's blowing up the equivalence relation written here. So you sort of have the positive quadrant, the negative quadrant, and then the origin. If you think of that equivalence relation, you've got like 2 squares joined at a corner with some point. That's not a smooth manifold. This equivalence relation is not a manifold. There's an issue at the origin. And what this groupoid G gamma is going to do is fix the issue at the origin and make it into a smooth groupoid.
Sorry, just to clarify something. We have a Lie groupoid here, this G of F. The algebroid associated to this is the module of the section of this algebroid and the vector field that you use to generate the Sussman foliation or are different in this?
Yeah, the algebroid can be identified with it's the like Serre-Swan dual of the F, curly F. So F is identified with sections of some Lie algebroid, and that's the Lie algebroid of the.
So it's not you cannot associate to the vector field that you used for the foliation.
No, it is associated.
Okay.
Sorry, maybe can you repeat your question? I feel like I didn't.
Just if the Lie algebroid of this Lie groupoid the section of this Lie algebroid correspond to the module that you use for generate the foliation. And this.
Yeah, but there's sort of two groupoids now, because it's like we have the ambient manifold and L, and like this thing is a groupoid on the whole of M.
On the whole,
The groupoid I'm describing here, I restricted to a transversal.
No, I was mentioning the geovet. I was referring to that.
But well, one reason I drew the picture actually was because you made me realize that I wanted to make a remark. So this equivalence relation is the leaf equivalence relation on the transversal, right? So if you restrict leaf equivalence, there's one class here, and there's one class here, and then there's this point, which is in its own class. So what I've drawn here is the sort of equivalence relation just restricted to the leaf equivalence relation restricted to transverse.
What do you mean by the smooth blow up?
Yeah, so right now this equivalence relation is a groupoid because you can sort of compose pairs and stuff like that, but it's not a manifold. So when I say blow up, I mean something's going to happen to the origin. I'm sure on the next slide. Something will happen here. Yeah, I don't know how to fix that. Maybe I should just go on. Let me see what's on the oh, it's gone. Maybe if I just switch tool a bit or something.
You have some kind of singular equivalence relation, and the smooth blow up makes it étal.
It won't be étal.
It won't be étal.
It won't be étal.
So what we gain after this smooth blow up, if it's not.
Well, I mean, we gain that we're smooth. Yeah, I mean, we gain that we're really looking at this Androbacchus scandalis groupoid now, which is sort of the proper proxy for the leaf space. You can, if we don't do that, we're sort of just looking at the leaf space, which is not a good space. Sorry, does anyone, organizer, know how to? I can't seem to change the page.
Oh,
I'm not.
Yeah, you should.
I'm stuck.
Try now. Oh, something is happening.
Oh, okay, it's working.
Yeah. Try again.
Okay. So
No, you have to.
You can always use the keyboard.
I think I have to put this to full page.
Yeah.
No, keyboard, Tomek.
Into page.
Tomek, can you hear me? Keyboard. Use buttons on the keyboard.
You can move it also.
It's working now.
But it's working now.
Okay, so basically I'll try to describe this blow up now. I've thrown a bunch of notation on the board, but so okay, gamma sits in K-1 jets here. But if you remember this extension I mentioned earlier, you can look at its pre-image gamma, which I've denoted gamma R in the K jets. So using this extension that showed up before. And I'll just draw topologically what's going on. Gamma is like a discrete group. So topologically it looks like that. And then gamma R is a one-dimensional group. And what is going to happen is a Lie group. So when I said blow up, there was this problematic point at the origin in this blow up, it'll get replaced by gamma R. So basically that countable collection of lines I drew earlier is going to get stuffed in where the origin was and somehow resolve the singularity. And you don't really need to talk about these foliations to talk about this groupoid. I'm just the way I've stated it here. If you take any subgroup of k-1 jets, you can make this groupoid irrespective of where you got that group gamma from, or anything like that. So how does this work? We need to glue in this group to these two sort of quadrants. And the way it works is maybe what you would expect. So basically, if you have an element of gamma R, which is a k-jet, and you want to sort of know whether a sequence converges to it, well, a sufficient condition is that if you take an element of gamma R, you can represent it by a diffeomorphism, theta. And then you can look at the graph of that diffeomorphism. And basically, this is sort of tangent groupoid type philosophy. If you converge like along the graph of that diffeomorphism, you're not going to go to the origin anymore. You're going to go to something in this blow up, and that something will be the k-jet represented by, this sequence of points will converge to the k-jet of theta. That's what's written on the board already. So I'll just.
So if I understand, so maybe this blow up is not a desingularization, but it makes this situation standard in a sense, with some.
It makes it
wider singularity.
Yeah. So you're sort of asking like why blow it up? I mean, it's so like if you draw the leaf space, right? So the leaf space consists of leaf space. It's like one leaf, another leaf, and the leaf in the middle, and then this is dense. So the actual sort of leaf space is a 3-point space with one dense point. And it's not really amenable to like doing much of anything. And somehow if you look at this equivalence relation, I mean, in the sense that two singular things can be like Morita equivalent to each other. I'm just basically talking garbage right now, but I feel like this, without doing the blow up, these things are probably somehow equivalently bad to one another. So we want to get a better object where we can do kind of analysis and find K-theory and stuff like that. But now that I've drawn that picture, maybe I should remark that the leaf space looks zero-dimensional. And that will be relevant because in Kahn's setting, you got like a class in K1 because it was sort of morally a one-dimensional leaf space. But here our leaf space is morally zero-dimensional. So our classes will be in K0 rather than in K1. All right, and more pictures, I'm not going to show you any formulas, but if I show you a few pictures, you'll probably believe that this blow up exists. So if the purple curves are like all diffeomorphisms with the same derivative, the blue curves are diffeomorphisms with a different but equal derivative. And the reason there are lots of curves is I've also put in some second order Taylor series differences. And when you make this groupoid, you basically have to make like different charts for all the possible sort of lower order Taylor series things that can go on. So, there's going to be like a chart which inserts a limit for all the purple curves and a chart that inserts a limit for all the blue curves. But the purple curves won't converge in the blue chart and the blue curves won't converge in the purple chart. Blah, blah, blah. More pictures. So yeah, here's a more sort of schematic picture of what's going on. You have this singular equivalence relation and you've covered it with this kind of blow up where the origin has been inserted with this one-dimensional Lie group. The one-dimensional Lie group has been inserted where the origin was. They're all sort of nested. If you have a gamma 1 contained in a gamma 2, the blow up will contain the blow up. And there's a smallest one, which is if you just glue in R, which is sort of gamma 1, if you like. R is gamma 1. And in that case, there's another way to think about that blow up groupoid, which is that you're just making a transformation groupoid. So that picture of the line earlier with a flow on it, you can take the transformation groupoid associated to that flow, and you'll get this picture at the top left. So sort of the G1, the smallest blow up is just a transformation groupoid, but it sits in all the other ones that can pass.
Doesn't make sense to speak about the system of blowups
I think probably
and
here.
the direct limits of this system.
Yeah, so basically, like you could do the largest possible, because here the system is the maps in the system are not that interesting because they're just containments. Like it's like if gamma 1 is contained in gamma 2, sorry, that's a containment. Then G gamma 1 is contained as an open subgroupoid in G gamma 2. So the maps are not like that interesting, and sort of the direct limit is just going to be the union of all of them, which is just going to be this R plus squared union R minus squared union all of JK. So all these groups that are being glued in are subgroups of JK, and you could take their union, which means gluing in all of JK. This is sort of like gamma all of JK minus 1, if you like. But when you do that, you sort of get a very large group, because remember the topology here is supposed to be as a one-dimensional E group. So JK is sort of like uncountably many cosets. So it's a bit of a strange thing to do. From that perspective, you end up with like a non-second countable manifold, but you can do a largest blow up, which I think is probably the direct limit you're thinking of. All right, so that's it for me explaining this blow up. So you're now supposed to believe that for every gamma in JK minus 1, you can make a blow up group. And now that's all old stuff. So that's the end of things from when I was in grad school. But I recently sort of dusted this stuff off because I was looking in particular at this containment in the middle and realizing that it's a little bit like what Kahn does. The fact that you have this one example in all possible groupoids kind of lets you push forward like whatever canonical K-theory classes you have here to here. And so I thought, why not sort of see if we can get something like transverse fundamental class in this context. Oops. So this is what it's not so bad, at least for the K-theory. So okay, you have a transverse order K foliation, you take this slice, and we're going to get a K0 class. Remember, it's a zero-dimensional leaf space. And the way that works is by, so you have your transversal. I don't know if I should draw a picture of something. I keep drawing the same picture. I don't think it gets more informative because I draw it more times. But the transversal has K-theory. It has a class in K1. And by Kahn-Tom isomorphism, cross product by R does a dimension shift. So you get a class in K0 of cross product. So what is the cross product? It's like the flow of this vector field y to the k dy. So that gives you a K0 class. But then this groupoid fits into this groupoid, G gamma. So you can map the K-theory class, and this thing was Morita equivalent to the whole polynomial groupoid in the sense of Androlodocus spindalis. So you have a way to take the orientation class of the transversal and map it all the way to this polynomial groupoid's K0. And you have to wonder, does it depend on choices? But it does not, and you can make this definition. So definition, the transverse orientation class is the image of the positively oriented generator of K1 in this way. There. So the goal, and did I say already? If I didn't, I'll say it now. This is work in progress. I sort of had this idea, but I haven't, written it up or even checked details, so it might be false. But my goal is basically to define also transverse fundamental class. So that's something in cyclic theory, and then pair it with this orientation class to sort of prove that this thing's non-torsion. So get a vector bundle. That would be what I'd like to do. So how would that look? I'll just sort of say that. So let me remind you, quantile isomorphism is this. A theory cross products by R are compatible in this way. A and A cross R have the same theory. And there's also this counterpart in cyclic theory due to Elliott-Matsumi Nest, which A became curly, but anyway, there's also a map when you take these sort of smooth cross products in cyclic cohomology of A, and there's a compatibility between them. So if you had a class that you were pairing at the A level, then you get a K-theory class and a cohomology class that you pair at the cross product by R level, and you'll get the same thing. This is probably extremely unhelpful if you've never seen this paper, but some tools are being used, I guess is all I'm saying. And there's this very intriguing formula that you'll find in that paper of Elliott-Matsumi Nest, which tells you kind of what you get in the case of translation acting on R. So C0R has a K-theory class, sort of the fundamental loop in K1, and there's a one trace that detects it, which is written here called epsilon. So you have a pairing between winding number loop 1 and this one trace, and you can map epsilon to a 2 trace, and you can map the loop to a projection, which is sort of I didn't write the cross product, but you get the compact operators in K-theory classes projection of rank 1. So there should be some 2 trace that pairs to give 1 with the rank 1 projection and the compact operators. And there's this intriguing looking formula involving the position and momentum operators and some like commutators, which looks kind of weird. I think like formally it's trying to be something like FDG. Like somehow you're supposed to, as I understand it, make a 1 parameter family of like R actions. And when it sort of becomes stationary, you want it to connect somehow to this 2 trace. And this is sort of the formula you need to use so that you can continue the family and hit like this thing, which is what you should get for C0R2. So the stabilization things. Suspension. I don't know, I shouldn't say more or I'll say wrong things, but yeah, so here we're not taking translation flow, we're taking something more like an Euler vector. So is there also a formula for the cocycle? Well, yes, there must be, because that paper has a construction of the map called, hashtag alpha. And so there is a construction, and therefore there's a formula for a 2 trace. And I think it basically works the same way as for translation flow. You just have to take the operators of the translation flow in different coordinates. So the D is going to become something like this, the generator of the flow. Here the vector field is not complete, so I'm probably glossing over some stuff. But anyway, and M is going to become multiplication by x to the k. So this is like, it's probably hopefully written down in a way so the commutator is 1. And my thinking is that I just wrote down the invariant measure for that vector field. So what I'm saying is that there should be a formula for a two trace that's on this cross product. And the operators D and M should be defined on a Hilbert space where this blow-up groupoid is also acting. So you can kind of use this same formula on those operators.
Sorry, I don't understand this formula. If you have this multiplication by X operator, M, capital M.
Yeah.
Then you interpret these functions, F, G, H.
Oh, yeah, these
as
function,
multiplications by functions. So
it's really, this is super badly done because, so what's going on is we've moved to the cross product.
Oh.
Which in this case is compact
yes.
operators.
Okay. Now you're
So really the F, G, and H are living there. So it's kind of funny. It's a funny.
now this will be non-trivial. This commutator with that.
There is something interesting going on here, which is that like. So there's also a zero trace that detects the K theory of the compact operators, which is just the trace. So why, here's a two trace, like why are we using a two trace? This is also gonna, you know, if I put in rank one projection E, I get one, but why need this two trace when a zero trace suffices? But I'm not really making too much sense, but basically like in this example, where we're sort of living, where now that there's isotropy, there's not like a non-singular invariant measure. So there's not really like, if you look at this cross product by this action, there's no trace on, this is sort of closer to Toeplitz algebra, and there's not a trace there. So there's never going to be like a zero trace here that detects the K theory. I'm jumping too many steps, but in my head, I'm thinking like, I have an algebra with a thing that can detect the K theory, and I need to extend it to a cocycle on a bigger algebra to detect the K theory. And it would be a lot easier if I just had a trace. If I had a trace, I could try and extend the trace to the ambient algebra. But I don't have a trace, is my point. So because of the isotropy, there's no trace on this algebra. So you're forced to work with something else that detects the K theory. It's two trace, and this two trace needs to be extended to the ambient algebra, which is just a more annoying thing to do than try to extend a trace. But my point, what I'm going to argue is there are formulas for this two trace, and they seem to also apply in the larger algebra. So you just need to check that these make sense and domains are okay. If you need to maybe do some like spectral subalgebra or something to make sure it's okay with the K theory. I haven't done any of those things, so I have no evidence to back up that this program succeeds. But yeah, that's sort of my thinking. You can probably make the fundamental class in that way.
Sorry, I have a question about this multiplication operator by X to the power K. But then of course, this invariant measure is defined. It's not well defined. What is it?
Well, yeah,
The group is a monoid.
the question is like, what happens when you apply this, like when you do something
Doesn't
like,
make sense to you.
like M, because it looks grim because of the singularity, but then if you, so you're trying to do something like commutator M with G, but and G is an element of something like CC infinity or C 0R. I probably should just make it compactly supported everywhere. And the action is involved. So the question is like, what does it do at that level? And you can check that. I've checked like a certain amount of stuff that the formula, for example, this is something plausible where like the radon-Nicodemus, the measure or something comes into play, and the singularity like doesn't show up when you look at how this commutator kind of unfolds. So things sort of look a little bit plausible. But that, I mean, so I'm not so concerned about what happens on sort of small subalgebra. But when you go to this blow-up groupoid, it becomes more well, I shouldn't sound pessimistic, I just haven't done it, but I'm not really so sure about whether these singularities in this measure, for example, cause issues when you try to start, rather than having G be an element of this cross product, have G be an element of this C-star algebra of this blow-up groupoid. That's kind of the fundamental issue is, well, does this sort of formula still make sense when G is living as a function on this sort of blow-up groupoid?
So all this makes sense for this smooth subalgebra.
Is the smooth subalgebra, you mean the like this cross product?
How do you extend it to?
Yeah, smooth subalgebra. I honestly, I can't really talk in good detail about this. This is more like a sketch than anything I've actually successfully thought about. But okay, I don't know what's coming next. I think that's kind of it for how I think the fundamental class should work. Hopefully it does and exists and pairs nicely with K-theory. If that doesn't work, then there are sort of pure K-theory approaches if you don't want to even try to make a cyclic cocycle. So there are some extensions you can make. So for example, I put the groupoid up again just to indicate that if I take an element of the groupoid, so some function that's defined here, sort of an element of the groupoid algebra, you can restrict it to gamma R, which is sitting here. So I just say that so that I can turn the page and have you believe that there are extensions like this. So an element of the groupoid C-star algebra can be restricted to this C-star algebra of gamma R. And the kernel is going to be, you have these paired groupoids, big from text. Going to be something like the compact operators. So this fundamental class that's living here, there's some element of interest that I'm trying to show is non-torsion. There are other ways of getting it, like the way it's coming to you is pushed forward from here in K-theory. But that class it's pushed forward from can also be pushed forward from here. So you can kind of come at it from the compact operators side. Like something like 1,0 here is another element that could be pushed to get the class here. So if you do that, then I don't think this is as interesting as trying to make a cocycle and get a nice formula, but you can do some K-theory stuff and figure out what is required to make your class non-torsion. So there are this is some index maps, and maybe I'll just slip past it and focus on the conclusion, which is that you can reduce the question of this. Oh, it's been written differently. So let me say it aloud. This thing I called the orientation class, and which I'd like to be non-torsion, whether that's the case can be reduced to index question. Let me just say it that way. There's a class, I want it to be non-torsion. There is an index map arising from the extensions on previous slides. And whether that index map does a certain thing that you expect it to do decides the question of whether the class you want to be a non-torsion is. That is also a valid approach, but
What does it mean? Then K0 of this is injective.
I know, I think this is a typo basically. I was copy pasting something.
The map induced on the level of K.
Yeah, I could cross it out. This can be replaced with, yeah, is injective, that doesn't mean anything. This could be replaced with this thing I call M mod F, which belongs to K0 C star. This blow up groupoid is non-torsion. I don't know what that is here. It doesn't make any sense. Is injective. But yeah, suffice it to say that question, which could be more interestingly answered by finding a co-cycle to pair it with, could also be answered by some sort of purely K-theoretic question. You know, like you have this extension and it has an index map, and if you can compute it, which in principle is kind of not hard because the group gamma is sort of solvable and you can use like you know, UCT is working here. So in principle, you can sort of compute everything about this extension. I say in principle because it just means that an expert could do it. It doesn't mean I could do it. But yeah, once you understand enough about a map, you should know at least the torsion yes or no question. But I strongly suspect that it's non-torsion.
So in particular, if the image is of the form d times 1, 0, you mean that it is torsion.
Yeah.
Right.
Yeah, then you get some torsion arises. Like it's sort of like if you like, if I go back to this picture, if I could try to put it in words, you can kind of basically make like a left. So if you take the way this works is you have sort of some symbol here, so an element of K1 C star gamma R, and you can kind of try to compute its index, and it has two indices because I've attached a positive half and a negative half. So there's kind of a left and a right index for every symbol that you take here, and basically you want to say left index and right index should be the same, or actually one is the negative of each other. It has something to do with the orientations of the vector fields. That was kind of what was, there was some cases that K is one, positive, or sorry, even odd. But you can essentially say the question is like this, yeah, things that you take from K theory of gamma R have two indices, one for the right half plane and one for the left half plane. And you want them to kind of, one index should determine the other in a predictable way. They should essentially be the same index.
So this sounds like there is some lattice, which is an image of this invariant, and that's two generators. Is it true?
Lattice. Do you mean lattice like of these groups or of something?
Yes, in Z cross C. How
as a K theory of this as K,
Sorry?
K theory of K plus K.
Yeah.
So it's two copies of that.
Yes. Yes.
That's it. Why?
Yeah, but torsion depends on very specific elements here, which are skew, like 1, 1, 1 minus 1.
Oh,
Okay, so this is about some sublattice in this Z cross Z.
I guess. I mean, so I think that it's a little bit, it might not be that. So actually, when I was making this slide, I considered burying this sign. Like I wrote here, I considered just burying it in the definition of the index. Like there's some sort of choice here about how you orient the right and left half line, and I kind of oriented them both kind of moving away from the origin or something like that. And if you sort of set things up differently, then I think you could even do away with that. There was a way I could have formulated it that would have made it look a lot less busy and just hidden this sign change. But yeah, I guess there's some lattice thing.
I mean, it's case, even or odd, probably you have something.
I mean, another way to say it is that in the simplest case where this is
it would be easier to understand what's going on if you could have an example of a torsion element and to show how this torsion is, for instance, related to
yeah, I buried the details. But what it comes down, so for the simple case where there's no sort of holonomy, basically, this index map has a certain range, and I'm basically saying that it comes down to saying that the range doesn't grow, like the range of the index map for gamma R must contain the index map for the C star R case, but it's not allowed to be any bigger. Basically, you shouldn't get any kind of off diagonal index. Yeah, I don't know a better way to put it than something like left index must equal right index is what it is. It's probably, I'm a little worried about talking about it too long because some part of me believes this is like not a very difficult question. And I'm not sure why I haven't been able to crack it. But if you know how to do it, you know, let me know. And I will be very happy. I'm not sure what's coming. I think I'm at the end of the time and I'm also sort of running out of slides. Yeah, so it just says.
You have 10 minutes.
Oh, I have 10 minutes.
Yeah.
45, I thought. Okay, yeah, basically 10 minutes. I've gone too quickly then, so that's kind of the end. Thanks for listening. Here are those same references that were there at the beginning. I guess I'll stop here and maybe I don't know, see what happens once I stop talking.
Okay, thank you so much. And let's continue with questions. Richard, any comment about your own paper?
Not at the moment, at the blackboard later.
Okay. So let's begin with questions. Any questions from Warsaw?
I would have one. There are some invariants of foliations which are called the secondary characteristic classes. Okay, like
Yes.
got beyond weight class,
Yeah.
which has very nice interpretation in terms of cyclic theory. Okay, can you leave this kind of invariants to K theory like you did here?
So a Gaussian invariant is a very normal thing to think of, I think, here, and I do hope. I mean, I sort of what I feel is I'm at I would like to get a Gaussian invariant for this context, but it's sort of a prerequisite for that is that you need to have the fundamental class set up first, so you can pair and get the number. I haven't really thought about what needs to happen, but I sort of, at least I sense that there are some of the things that need to be present are here. So I sort of hope that if this part of it works, which might not, it might just be that the K theory is torsion or something, then hopefully the next step would be to look for something like Gaussian invariant. And I think you said like the same thing, because I described to Professor Gorkowski this work a little bit a couple days ago, and he also was like, well, why aren't you looking at Gaussian invariant? And I just, I wanted to, I hope to do that.
But beyond the invariant for singular foliations, so I know nothing about this.
I would have to look at, so there are people working on like characteristic classes and things for singular foliations.
So is there the
last time I looked at that, it was like,
Dawkins and Scandalis extension of?
So there are things like, I know I looked somewhere as people had things kind of like the bot connection, bot element. Is that, no, that's not what I want to say. What do I want to say?
There's of course bot connection.
But then the bot connection yields, what do you call it?
But in the singular case, is there an analog of bot connection?
There are things like that. In fact, bot connection is kind of like in the background here. That group that you know, like I have this map seems to be behind it all, right? It's just out of batteries.
The transversal, integrable part of what connect.
This is like some sort of lift of, oh my God. Probably doesn't matter, I can just leave it that way, but so this thing, oh, it goes here to T-1, but there's a derivative, right? So it's this thing, if you remember what it is, it's basically some Taylor series of a diffeomorphism, and you can just remember the derivative if you want. And I think in my thesis or something, I go so far as to call that composition the bot connection. Because it sort of is that it's like, you know, you're going around a loop in this singular leaf and you get some sort of expansion contraction data. So this is sort of like the fact that you remember a T-1 jet is some higher bot connection. You remember more derivatives.
So it's the higher order.
Yeah, the bot connection is in the picture, and there are also some like principal bundles and things in the picture. So there's some stuff going on, but I'm not really too familiar with it. I'm worried that there are different kinds of characteristic classes at play here, and I might be mixing up two different kinds of characteristic classes. But I'm depending on what your question is, I think it might have an answer, or I might just not know.
It would be interesting to see how much these results could be obtained from analyzing this ramified covering, desingularizing your foliation.
Yeah, you were saying about
because then you can lift everything to the regular situation.
But surely then see their own leaf. I don't know. Wouldn't there just be one leaf at that point, or I don't know what?
Probably not. It's like raising Y to some power, so you will obtain some ramified covering along this L. And something.
I don't know anything about that. But maybe this is a comment I should be
taking the comments, of course.
Okay. Yes. Thank you. Yeah.
Yeah. Anybody else from Warsaw? Okay, no volunteers. So how about folks from Zoom? Adam, you haven't asked a single question yet.
So maybe let me ask about von Neumann algebras. So do these singular foliations give rise to some interesting, for example, type 3-1 factors? Or?
That was exactly a question I wanted to ask.
That's a great question. I don't know. Yeah, I guess you want to know something about the different types of dynamics. I would suspect kind of no, and that's because somehow all the holonomy here is living in that solvable Lie group. Like everything, this is kind of a toy example. Like I devised this class of examples just to sort of do something with the Androlodacus construction that felt kind of hands-on. But all the holonomy is living inside this solvable, almost nilpotent Lie group. So I feel like the dynamics aren't somehow the discrete part of the dynamics aren't that complicated. So maybe the most interesting von Neumann algebras are unlikely to appear here, but of course there should be some von Neumann algebras that can be attached to this setting. I think that's about all I'm able to say.
Okay, thank you so
Thank
much.
you.
Adam, are you happy?
Yes. Okay, I'm happy with an answer, but okay, it would be interesting to obtain some exotic type 3-1, for example.
Yeah, I think it comes from an also.
I'm happy with an answer, but I'm not happy what it turned out to be.
Yeah, well, I mean, the thing is that I only have kind of codimension 1 here, and you know, there's a lot of other codimensions past 1, and when you start looking at them, you have a lot more sort of potential for, you know, weird things like free groups and so on appearing in the discrete part of the polynomial. But I think codimension 1 is too restrictive to get really weird groups. Not that the free group is weird. I don't want to insult anyone.
Okay, great.
I have a
Anything else?
question.
Mark,
Yes.
Elmar, Francesco? No.
I ask another question.
Go ahead. Go ahead.
Did you try the case when L is 0-dimensional?
That was in the very beginning, wasn't it?
Yes, you started from this, but
Well,
how far you can go
in a sense,
in this case?
well, there's no holonomy in the true 0-dimensional case, but in a sense, what's happening here is very 0-dimensional because, you know, I use the ambient manifold only to the point of getting the holonomy, this map that's I've coincidentally written on the board. But then, you know, after that, I restrict back down to the transverse. So it's basically like I'm studying the original 1-dimensional example, but now a bunch of extra holonomy has been kind of added that doesn't really, it's not really there because it came from ambient global stuff. So I'm not really sure what I'm saying. Your question was, have you looked at the 0-dimensional?
If L is 1-dimensional, there is possibly the situation that transversal can somehow accumulate around this singular locus.
If L is 1-dimensional? Do you mean 1-dimensional or 0-dimensional?
No. So I'm trying to distinguish these two cases, 0-dimensional and 1-dimensional. What kind of geometric phenomena could distinguish these cases? One, this 0-dimensional case of L, 0-dimensional. Why this is trivial, and in 1-dimensional case,
Well, there's no
non-trivial.
Well, there's no path. I mean, you can kind of artificially insert holonomy,
But is it about? Yes.
but there's no. I can't draw as, but yeah. I mean, if you want your holonomies to kind of come from running around the leaves and not from just sort of be it, like you can sort of introduce more holonomy transformations and bake them into your groupoid if you want. But I would just say that, you know, without a leaf to, you know, run around in, then you can't really get any kind of thing like classical holonomy.
Picture of this blow up, you have an interplay between this L, which is 1-dimensional, and these curves.
My L is sort of 0-dimensional.
No. In 1-dimensional case.
Yeah, but is it M or is it L that's 1-dimensional?
No. You have this case of L, which is 1-dimensional. Or codimensional. Sorry.
Yeah, codimension.
Codimensional.
Oh, maybe you're talking about codimension.
Yes, codimensional, yes.
Oh.
Yes, your pictures were 2-dimensional, so
Yeah.
I see it as the 1-dimensional. Okay, of codimension 1. But what if you have higher codimensions? So
Yeah.
So I'm thinking only about this 2-dimensional case. Okay. So
Yeah, I mean, once you go to higher codimension, there's a decent amount of variety. Like this groupoid of Angelidatus scandalis, all kinds of crazy things can happen. I mean, in particular, anything from regular foliations can occur. But so let me just make this remark. One striking thing that happens when you go from regular foliations to singular foliations is, whereas before holonomy was purely discrete, you have only discrete holonomy transformations, a discrete group at each kind of point. You get Lie groups in the singular case, you know, that like even this group gamma R, it's a 1-dimensional Lie group. So you have these sort of continuous holonomies where you're not really going around a loop, you're just doing some sort of flowing around the vector field with a critical point or something. You're getting kind of continuous holonomy that sort of survives into your Lie groupoid. So I would sort of say the discrete holonomy, you can kind of already see it in the regular case. So if you're sort of serious about singular foliations, somehow it's tempting to, I mean, you want to at least be mixing the continuous holonomy and discrete holonomy, or maybe even just like focusing on like you can get a lot of interesting groupoids even by just having like a one leaf point. You know, you can have all kinds of group actions that fix a single point.
Yeah, on the plane, the Euler field, for instance.
Yeah, so when a point is fixed, kind of all the holonomy which occurs at that point is going to be like Lie of a sort of continuous type holonomy, and rather than discrete. So there, I don't know. It's kind of like why study singular foliations and then do things that arise in classical setting. So maybe it should be more like a singularity theory kind of enterprise than you know. Just, I mean, I say that, but like everything I did here definitely used discrete holonomy. So I don't want to, you know, I'm basically solving my own sort of decision.
I'm thinking about this zero-dimensional case, because then I would expect something depending on this set of, let's say, finite or discrete set of points equipped with some orientation. Okay. And then I would expect some invariant in K0. Okay.
Oh.
It's something like you have pi1 of L, because in two-dimensional case it's one-dimensional. So you can speak about pi1. If you have a discrete set of singular points of this foliation, you can speak only about pi0. But maybe there is some primitive invariant taking values in K0. I don't know.
Yeah.
Maybe
I keep wanting to draw, but
not very.
Yeah, I mean, just in full generality, if you're on a manifold and you have one of these Stefan Sussman foliations and you fix a point, this groupoid GF, I mean, there is a isotropy group at this point, which is generally a Lie group. So it's going to be some, I don't know, I'll call it H, but H has a component group, you know, like H mod 80. And my instinct is that the way it kind of works is that the sort of quotient of disconnected Lie group by component group. So that's some discrete group. That's kind of what gets from classical types of holonomies. So you go around loops and stuff like that, and you get sort of discrete holonomy transformations. So these kind of things arise from like regular foliation techniques.
Yeah, but
and it's what happens in H0. It's what happens in
field of the form in polar coordinates r to the power k d over dr.
Yeah.
Then you have higher multiplicity at the singular point.
Yeah.
And you could expect that under this definition of holonomy, you will land in some.
Yeah. Yeah, in that case, because it comes from a group action, the holonomy groupoid will be transformation groupoid.
Okay.
The holonomy group would just be the Lie group, the one-dimensional Lie group, I guess, that flow of this vector field. But I mean, it's a very intriguing construction. I do encourage people to read this paper of Angelidakis Vallis. And you know, there's lots that's happened since 2009 since that was written. Because there's quite a bit there. It's just yeah, I mean, I would say that the examples I sort of waved in front of your faces today are extremely simple examples, but there's still a bit you can do there. And yeah, once you start looking at more complicated foliations, things get very interesting indeed. all the phenomenon from the regular setting is still there, but there's also this sort of continuous holonomial that's kind of playing around as well.
I remember that in the case of foliations, there is some equivalence relation, which is much coarser than being conjugated by the diffeomorphism. It's called concordance. Okay?
Mhm.
And many invariants of foliations are not only invariants of diffeomorphism type, but they are invariants of this concordance type.
Yeah, I admit I don't know the definition of concordance.
So it sounds something like you can construct a smooth family of foliations, and you are asking whether your invariant is constant for all fibers of this family.
Like
Yeah. So I know that some invariants like Godbion-Weil could vary if in continuous families. Okay, but I don't know what is happening in your case.
I mean,
If your invariant
variant is Bordism. Variant. Is concordance weaker or stronger than Bordism? You know, or do you know how they're related?
Concordance is stronger because it requires it's like a Bordism, but with division into these fibers.
Yeah, I think Godbion-Weil.
But if this is an invariant of cobordism, that is even better.
Yeah, that's interesting. I haven't thought about any Bordism stuff. I think, yeah, once if I can hopefully include this at some point for myself, then I'll certainly look at Godbion-Weil invariant. Maybe absolutely nothing will happen with this sort of set of examples, but if it does, then maybe I'll think a bit about what Bordism means at that point, or concordance even.
If you have cohomological invariants, in this case, factoring through the RAM cohomology, it's easy to check if something is invariant with respect to a smooth cobordism. But if it takes values in K-theory or I don't know in cyclic cohomology, you know, maybe it's an open question.
I don't know.
Okay.
Thank you.
So to end with, let me ask you a very straightforward, simple-minded question. If you don't mind, can you remind me what an n-trace is? The formula for an n-trace, you're using one traces, two traces. What is an n-trace on an algebra?
Well, to my mind, when you say n-trace, you're also including all these sort of domain issues or worrying about continuity and things like that. But I guess if I interpret the question as algebraically,
yes,
what are the conditions, then I guess you can sort of give the Hochschild homology type answer to that. Like it's a n+1 linear functional.
Sorry, it is n-cyclic cycle.
Yeah.
it's just n-cyclic cocycle, right?
N-cyclic cycle.
No.
Sorry, an n-cyclic.
Cyclic.
Yeah, but an n+1 linear functional on the algebra with satisfying through like 2 or 3 axioms. I don't know. I'm sorry. I don't know. I don't want to.
It's solid cyclic circle. Yes.
And I'm afraid to write the wrong things or something about it. If I had a bit more board, maybe I could try to.
Yeah. Please write. I mean, you can go to some less less dense page and.
It's really almost. Try now. Yes.
Oh, I really polluted so many of these.
Oh, here I have lots of empty space in the middle.
So something like 5. Satisfying
Yes.
like some, conditions with a summation of. Yeah, these things are always hard to write, I guess, because you need to multiply at the ith stage or something. This should be 0, like this.
Ah, so this means the effect of
Oh,
it's not cyclic.
what am I?
Plus,
One of the axioms.
it's one of the properties.
You need one,
You need a round, I need a wrap.
Relation come with.
Wraparound term. Should be 0. And then what else? So if you do cyclic permutation, it matters like the parity of n, I suppose. It
It
should
really
be.
is an cyclic cycle, right? I mean, it's
Yeah.
okay.
It's
Okay,
cycle
okay. I know what an encyclic
sorry.
cycle is. So why on earth call it
I
an
thought you
entrace?
wanted me to write the definition of encyclic cycle. Yeah, sorry, that's just another terminology, and it might just be in my imagination. But when I say entrace rather than cyclic cocycle, I'm sort of thinking that maybe topology is entering.
No, it's
None of them.
literally a cyclical cycle plus we satisfy certain boundedness conditions. Which
Yeah,
allow
okay.
extension.
So it's not just in my head then.
It is something like this.
Cyclical cycle plus some analytic boundedness.
Yeah. plus-
Okay. So I'm happy I asked this question. Okay.
For example, there was that curly A that showed up very, very briefly, and it,
Mhm.
the kind of curly A should have the same K theory, for example. So it should be one of these like spectral
Mhm.
subalgebras.
Mhm. Mhm.
I mean, for practical applications, you want those kinds of things to be happening.
Okay. Okay, thank you so much for clarifying this and for your very interesting talk. So let us thank our speaker again. Thank you so much. And I stop recording.